Hi, in this video, I'm going to talk about question number 1 of homework 10 of probability and stochastic processes course. In the first question, we want to talk about some examples of stochastic processes and their features, their probability masses or density function, mean, and autocorrelation functions. The first one is the Poisson process. So the Poisson process is the probability uh, of so the probability of the number of calls, for example, received in t hours. So we have x, which is the number of calls, and we have t. And we know from the first part of the course that the probability uh, uh, distribution function of Poisson process is equal to the sigma of e to the power of minus lambda t times lambda t to the power of k and k factorial in the denominator. And now we want to calculate the mean of the Poisson process. To calculate the mean, we know that the sum of Poisson process from 0 to minus to plus infinity for k is equal to 1. So the sigma of lambda t to the power of k and divided by k factorial is equal to e to the power of lambda t. And then we take the derivative of both sides with respect to lambda t, and we get to this term. So by doing that, now we can calculate the mean, which is lambda times t. And now we want to calculate the autocorrelation. So the autocorrelation, to calculate the autocorrelation function for Poisson process, we should do some trick. And our trick is that we know that if we know that T2 is greater than T1, we know that the Poisson process between for time 0 to time t1 and the Poisson process for time t1 to time t2. These two time ranges, because they don't have any core overlap, they are independent of each other. So the probability of the Poisson process in time 0 to t1 times the Poisson process in time t2, t1 and t2 is equal to the expected value of the first term times the expected value of the second term. And that's really easy to calculate because we have the mean of the Poisson process, which is lambda times t, and we know the answer. But we want to find the autocorrelation between t1 and t2, and uh, we know that the number of that incident of Poisson process between time t1 and t2 is equal to the number of time that specific incident has happened between 0 and t2 minus 0 and t1. So the n of t1 and t2 is equal to x of t2 minus x of t1. Just let me check if the video is correct. Yeah. So now we can write the expected value of n of 0 to t1 times n of t1 to t2 is equal to the expected value of x of t1 times x of t2 minus x of t1. So if we do the multiplication inside the expectation operator, we will get to r of t1 and t2 minus e of x1 to the power of 2, which we know the value for the left side and the rightmost term, so we can find the value of r of t1 and t2, which is the expected value of n of 0 and t1 times n of t2 and t1 and t2 plus expected value of x1 to the power of 2. Okay. Uh, Let me change this to single page. And so uh, so we calculate the probability density distribution function, autocorrelation, and mean for the Poisson process. The second one is Poisson increments. Sorry, the Poisson increments has the formula which is like this: x of t plus epsilon minus x of t divided by epsilon. Okay, so if we want to calculate the probability distribution function of this, we will write the probability of y of t being equal to n divided by epsilon. And if we do the multiplication uh, of epsilon to both sides, we get the probability of epsilon yt equal to n. And we can substitute the y of t with the formula which we have for y of t, and we can write it like this. And again, we came to the Poisson process, which is from time t to time t plus epsilon. So the delta time is epsilon, and the probability density function is going to be this. Exactly the Poisson process, just substitute t with epsilon. So we know that so this is the probability distribution function. Let's go to the mean. To calculate the mean, we will write the expectation of y of t, and we will substitute y of t with the formula which we have, and then we can and then the 1 divided by epsilon comes out of the expectation, and we know that um, uh, okay, we know that the sorry okay, let's get back to the problem. And we know that the expectation of x of t plus epsilon minus x of t is equal to lambda times epsilon, and we have 1 divided by epsilon, so we get to lambda. And for the last part, we should calculate the autocorrelation function, and we write the formula of autocorrelation, which is the expectation of y of t1 times y of t2, and we will substitute y with the formula which we have here. And because the times, okay, now in this part we should do some we should do some assumption on the T1 and T2, whether they have any overlap or not. So at the first point, we will think of a situation that T1 and T2 do not, T2, the range T2 to T2 plus epsilon, and the range T1 till T1 plus epsilon. We think of these two ranges in a way that they don't have any overlaps. And because they don't have any overlaps, so we know that the Poisson processes are independent, and the expectation and the term in the expectation comes out of it. And we should, so the expectation of the first part is lambda, and the second part is lambda, so it is lambda to the power of 2. But we can think of a situation when these two parts have some overlaps. And we for the first scenario, we think that T1 and T2 have overlap, but T2 is smaller than T1, and T1 is smaller than T2 plus epsilon. Again, we write the expectation and uh, we do the multiplication of two terms, and after doing a lot of calculations, we see that some terms are removed because because they have plus and minus and all of these, and then we will get to this part. But we had some assumption that T2 is smaller than T1 and T1 is smaller than T2 plus epsilon. But we can do it another way, that T1 is smaller than T2 and T2 is smaller than T1 plus epsilon. And we should write the final answer with some absolute value of T1 minus T2. Okay, so let's go to the third one. The third one is Poisson impulses. What is Poisson impulses? So the Poisson impulses is the derivative of Poisson process with respect to t. And because derivative is a linear operation, we can bring it out of the expectation operator, and we after doing and when we take the derivative of lambda times t to the with respect to t, we get to lambda. So the expected value is equal to lambda, and now we should calculate the autocorrelation. The autocorrelation has a formula like this, which is the expected value of z of t1 times z of t2. Let me check if the video is recorded. Okay, so we are doing fine. Okay. Um, so yes, I was talking about the autocorrelation of z. And again, the derivatives come out of the expectation operator, and we know the autocorrelation for x, which is a Poisson process, and we write the formula and we take the derivatives and we can have the autocorrelation. In the fourth part, we have semi-random telegraph signal. The semi-random telegraph signal. What is that supposed to mean? Okay. The formula is this. If the number of events from the Poisson process, if the number of events, the k, is even, we put 1 for our new Poisson part for our new stochastic process, and -1 if the k is odd. Okay. Now, at first, we want to calculate the probability distribution function. So we should calculate the probability of x of t to be equal to 1. And this is equal to this, that the probability of the k to be 0, 2, 4, 6, 8, and all odd numbers. Sorry, and all even numbers. And we do the sum over all of these probabilities, and we get to the e to the power of minus lambda t times cosine hyperbolic of lambda times t. And the probability of x of t to be equal to -1 is equal to the number of times for the Poisson process to be odd. So we have another sum over the probabilities that the k is, for example, 1, 3, 5, and all of them, and we get this term, which is e to the power of minus lambda t times sine hyperbolic of lambda t. And the expected value for this is 1 times the probability that x of t is 1, and -1 times the probability that x of t is equal to -1. And after doing all of this, we get to this part. Okay, let me get back. Okay, now we want to calculate the autocorrelation for this part. To calculate the autocorrelation, we should calculate the expected value of x of t1 times x of t2, which is 1 times the probability of the x of t1 times x of t2 to be equal to 1, and -1 times the probability of x of t1 times x of t2 to be equal to -1. So this is also equal to the probability that k is even in the time range of t1 and t2 minus the probability of k to be odd in the range of t1 and t2. And we have all these probabilities, so we can substitute them and we will get to a result. But because we had some assumption that t1 is greater than t2, if we now consider that t2 is greater than t1, we will get to the same result with some minus in the power. And so our last result is this: e to the power of minus 2 lambda t1 minus t2. Okay, the fifth part is the random telegraph signal. The random telegraph signal, to, to define this, we need to first define the random variable, which is equal to 1 with with some probability, and equal to minus 1 with some probability, and these two probabilities are equal. So so this is a random variable that is, for example, Bernoulli, and p is equal to 0.5. And we will define the random telegraph signal like this: y of t is equal to a, which is a random variable, times x of t. Okay, to calculate the probability distribution function, we first think of a to be greater than 0, and we write the probability of y to be smaller than y. And again, we can substitute the y, which is a Poisson process, with his formula, and we can find the f, which is the probability distribution function of x. And for if a is smaller than if a is smaller than 0, it's a negative number. The calculation is a little bit different that you can see here. So we calculated the probability distribution function. Now, if we go through the problem to calculate the mean of this stochastic process, we say that we want to calculate the expected value of a times x of t. And because a and x of t are independent, we can bring a out of the expected value, so we have expected value of a times expected value of x of t. And because we know that the expected value of a is 0, so this is 0 as well. And for the last thing, we should calculate the autocorrelation for y of t. Just let me check if the video is recorded. Yeah. Okay, so we should calculate the expected value of a to the power of 2 times x of t1 and x of t2 again. Because we know that a is independent from x, we can bring it out of the expected value, and so it is equal to the expected value of a to the power of 2 and times r of x, because we know that the expected value of a to the power of 2 is 1, and we have the value for the autocorrelation of x from the previous parts. We can just write them down, and that's finished. Okay, let's go to the sixth part, which is random walk. Very interesting. Okay, so in the random walk, with some probabilities, we are going to be in so in the random walk, um, let me check my answers. I want to start from the Okay. In the random walk, we are doing n steps, and in these n steps, in for example k steps, we are observing a head, so we are going to the plus one, and with the n minus k we are observing the tail, so we are going to the minus s. And if we want, so this is the formula, but if we want to calculate the probability distribution function of x to be equal to k, we can think about this as a binomial distribution. So we have this formula, which is the formula of binomial, and then we know that the p and q are equal to each other, and they are 1 divided by 2, so we can write them down very easily. And but for the random walk, we have the same thing, but k is equal to the n plus r divided by 2. So we are using the binomial distribution, and we are defining the k for the random walk as it is. Uh, okay, so we calculate the probability distribution function. Now we want to calculate the expected value and the autocorrelation. So we should define some notations, and then talk about it. So y of I is a random variable, and at the time t equal to I times t, we know that y of I is s if we observe head goes to s, and goes to minus s if we go to tail. Okay, so sorry. So the expected value of yi is equal to 0, because with the same probability is it might go to s or minus s, and these are 0 together. Sum of expected value for this is 0. Okay. And the expected value of yi to the power of 2 is equal to s to the power of 2. And because yi and yj are independent of each other, we know that the expected value of yi and yj is equal to the expected value of yi times expected value of yj, and it's equal to 0. Sorry, because the video is very long. I just lost my energy. Okay. And we can define the x of n times t as the sum of all these yi's, all these steps. Okay, so the expected value of x of n times t is equal to the expected value of sum of all these y's, and sum is a linear operator. It comes out of the expectation, and because we know that the expectation value of yi is equal to 0, so sum of zeros are 0. Okay, so the expected value of x to the power of 2 is the expected value of the sum of yi's to the power of 2. And if we write them down, because we know that yi and yj are independent and their expected value is equal to 0, we can forget about them, and only we have the sum of expected values of yi to the power of 2, and we have the expected value of yi to the power of 2, which is s to the power of 2, so we have n times s to the power of 2. Okay, now we get to the hard part, which we want to calculate, the autocorrelation. And for the autocorrelation, we assume that if m is greater than n, the expected value of x of n t times x of m t is equal to the expected value of sum of yi times sum of yi and yn plus 1 till m, till ym, because we know that m is greater than n. And again, because of the independent property that we have, all those expected values within this is 0. So again, the autocorrelation is n times s to the power of 2. We had an assumption that m is greater than n. Because of that, we have this. So if m is smaller than n, we will get m to the m times s to the power of 2. So then we have the minimum of n and m times s to the power of 2. And hopefully we are in the last part of this question, which is part 7, which is Wiener process. We want to talk about Wiener process. Let's see what is the Wiener process. So Wiener process is the random process, but the limiting process of random process. So W of t is equal to the limit of x of t, and s goes to 0, t goes to 0, and n goes to infinity. So it is like that. We are talking about random walk, but we are talking about the random walk for the after some times. And sorry, for t goes to infinity and n goes to t goes to 0 and n goes to infinity. Okay, if we want to calculate the expected value of w to the power of 2, we will have the limit of expected value of x to the power of 2 and limit of n times s to the power of 2. And we will just add some t to both nominator to the both parts of our fraction, and then we will substitute n times t, capital T, to small t, and after calculating the limit, we are going to that is going to be equal to alpha times t, and alpha is a constant that we have used for the case of s to the power of 2 times t, s to the power of 2 divided by t, big T, capital T. And now now that we have done this pre-process, let's talk about the probability distribution function of w. That we write that p of the probability that w of t is smaller than w, and we will substitute this with the limit of x of t, and again the limit comes out of the probability, and we will get to this formula that we had for the random walk, and we'll get this formula for the probability distribution function. And after that, if we calculate the derivative, we will get to the probability density function. And for doing the expectation, we again bring the limit out of the expectation operator and we will get to 0. And the last thing that we should do is to calculate the autocorrelation function. And again, the limit comes out of the expectation. And we had the autocorrelation for random walk. We will just substitute and we will get to the min of t1 and t2 times alpha, which is a constant. That was question number 1. Thanks for listening to me.